Hello, linear algebra students. Today's video lesson is on the topic of vectors. Now, a vector is a mathematical construct that has two features. One is a direction, and two is a non-negative magnitude. Magnitude just means an amount. An example of a vector is a force, which has both direction and magnitude. So there's an amount of force, and there's a direction in which the force is being applied. Now, a construct with a magnitude only is called a scalar, such as the mass of an object, which has no direction. Now, vectors are graphically represented as arrows, beginning at the tail, or origin or starting point, and ending at the head, or end point, and whose length represents the magnitude of the vector. Typically, vectors are symbolically represented as bold letters or letters with an arrow accent, such as a bold V or a V with an arrow above it. A two-dimensional or 2D vector has directions limited to a two-dimensional plane, and a three-dimensional or 3D vector has directions limited to three-dimensional space. If the tail of the 2D or 3D vector were situated at the origin, then the vector can be represented by the coordinates of the head of the vector, called the components, in any of the following ways. So let's first consider this two-dimensional situation. I have a vector u depicted in the image. This vector has a direction and a magnitude, and it has the same direction and magnitude no matter where I position it. So one thing to keep in mind is that no matter where the origin of the vector is, as long as it has the same direction and the same length, then it's considered to be the same vector. Now, if you were to situate this vector u so that the tail is at the origin, then the location of the head of the vector, which would be here, would have coordinates, in this case, 5, 2. Thus, we can say that the vector u has components 5 and 2. And we can write that using these angle brackets, 5, 2. Or we can write this as a column vector, 5, 2. Or the transpose of a row vector, 5, 2 transpose. Any of these is acceptable. Now for the second vector v, if we position it so that the tail of v is at the origin, then the coordinates of where the head is located, which would be right here, would reveal the components of this vector. And this would be at location left 1 up 3 from the origin. So we can say that vector v has components -1 and 3. And you can write that as a column matrix or as a row matrix with a transpose. If I reposition my frame of reference to being like this, then our vector v would have a tail at -1, -1, and a head at -2, 2. So vectors don't necessarily need to start at the origin, but this vector would still have components -1 and 3, because to get from the tail to the head, you would go left 1 and up 3. Now you might notice that if a vector connects 2 points in the plane, you can simply subtract the y coordinates of the points to get the y component of the vector, and then you can subtract in the same order the x coordinates of the points to get the x component of the vector. But again, regardless of where this vector v is situated relative to the origin, its components are -1, 3. Now in three-dimensional space, we need 3 components to establish a vector that has both a direction and a magnitude. Now, unless we're able to rotate this three-dimensional space, it can be confusing using a two-dimensional image to detect the direction of the depicted vector w. Currently, this vector is depicted originating at the origin. This vector w could be moved anywhere, and it would be considered the same vector because it still has the same direction and the same length. But now that vector w is positioned at the origin of the x, y, and z axes, we simply need to determine what would be the coordinates of its head. So in the x direction, we go 2 units in the positive direction, so x will be 2. But then we go in the y direction, we go in the negative sense, so -1 in the y direction. And then we seem to go up from there, so z will be positive, and the question is, how far up do we go? Now, in this image, it can be difficult to determine that. However, if I copy this parallelogram at the bottom and move it up, this can give us a good indication of exactly how high we are by tracking where our parallelogram hits the z-axis. So it appears to be at a height 3. So this vector will have components from the tail. We go 2 units in the x direction, -1 units in the y direction, and then 3 units in the z direction, which you could write as a column vector instead, or as a row vector transpose. It can be helpful to use a three-dimensional grapher to visualize three-dimensional vectors. If you go to Google and search Calc Plot 3D and click the first link you find, you should find this webpage. It defaults to a graph already being present. I'm going to hit this X to get rid of it. Then I'm going to select and add a vector and put its components in here. The components of the vector W were 2, -1, and 3. And then I hit enter, and it makes such a vector that you can then rotate the imagery to see the vector from a variety of points of view. You can change its initial point if you like. You can change the width. You can change its color. And then these buttons give you ways to control the window in which you view the space and other viewing options. Okay, let's go to the next page. The magnitude of a 2D or 3D vector v is represented by, and you put the vector v in what it looked like absolute value bars, or you could do double absolute value bars. For this course, we'll just use single absolute value bars. And it is given by the formulas below. So the magnitude of a two-dimensional vector is simply the square root of the sum of the squares of its components. And that generalizes to a three-dimensional vector. The magnitude of a three-dimensional vector will be the square root of the sum of the squares of its components. These are really just variants of the Pythagorean theorem being used. Determine the magnitude of each vector depicted in the images below. For vector u, we go in the x direction, 5 units, and then we go in the y direction, 2 units. You can clearly see that in the two-dimensional case, this simply makes a right triangle. The magnitude of this vector is the length of the hypotenuse. Hence, we have the Pythagorean theorem being used, and we get that the magnitude of vector u is equal to the square root of the sum of the squares of its components, which are the two legs of this triangle. So 5 squared plus 2 squared, that gives me square root of 29. For vector v, regardless of where the tail is, from the tail we would go left 1 unit and then up 3 units. So its components would be -1, 3, and its magnitude will be found by using the Pythagorean theorem. The magnitude of v will be the square root of, and then square the components and add them together. Notice the fact that the first component is negative has no effect, because when it gets squared, it's as if it was positive. And we get a square root of 10 for the magnitude of vector v. Let's go to the next page. Scaling vectors. The opposite of a vector is another vector with the same magnitude but the opposite direction. Also, vectors can be scaled by positive scalars to change its magnitude without changing its direction. Scaling by a negative scalar will scale its magnitude and also result in a vector going in the opposite direction. Given the two-dimensional vectors u and v below, draw and give the components of the vectors that follow. Note these concepts generalize to 3D vectors. So focusing on this first one here, the opposite of vector v. The opposite of v is a vector that has the same magnitude as v, but goes the opposite direction. So focus on this image of v. Make a vector that has the same length, but change the direction of the arrow. And this pink vector is the opposite of v. And it doesn't matter where you position the pink vector, it has the same direction and magnitude. So it's always the same vector no matter where you originate it. But wherever you do position the opposite of v, you will go right 1 unit from the tail, followed by going down 3 units to get to the head. Notice what vector v was. And we can see that the components of the opposite of v are the opposite of the components of v, suggesting that to compute negative v, we can do negative, followed by any version of our notation, including the angled brackets for vector v, and then essentially distribute the negative, thereby changing the signs of both components, giving us the components of the opposite of v. Now, 2 times v can be calculated by doubling the components of v, and distribute, and we get -2, 6. Visually, doubling v keeps the same direction as v, but doubles its magnitude. And you see, to go from tail to head, you would have to go left now 2 units, followed by going up now a total of 6 units, confirming that doubling the components produces a vector that keeps the direction, but doubles the magnitude. Now 1/3 of v will be a vector that goes in the same direction as v, but has 1/3 of its magnitude. Finding its components is done by finding 1/3 of the components of the vector v. This time I'll write vector v in column matrix form, giving me -1/3 as the first component and +1 as the second component. So we would only go left 1/3 and then up only 1, and it would produce this vector. Now finally, let's do -2/5 of u. We simply have to do -2/5 times the components of the u vector. The u vector had components 5 and 2. Multiply each component by -2/5, and we get -2 and -4/5. Visually, what's happening here, let's first find 2/5 of the vector u. Since the first component is 5 units long, 2/5 of 5 will just be 2. So we only need to go to the right 2 units and then up to get back to the same line segment. Therefore, this vector is 2/5 of u. If I want to do -2/5 of u, I would then need to copy this vector and change its direction, creating this orange vector, which no matter where I position it, it is -2/5 of u. So in summary, multiplying a vector by a positive scalar will keep the exact same direction, but simply affect the magnitude. But multiplying a vector by a negative scalar will reverse the direction and also potentially scale the magnitude. Let's go to the next page. Adding and subtracting vectors. Adding or subtracting vectors is as simple as adding or subtracting the corresponding components. Given the 2D vectors a and b below, draw and give the components of the vectors that follow. Note that these concepts generalize to 3D vectors. So we first have to come up with the components of a and b. Now for a, to go from tail to head, we would go left 3 and then up 1. So its components would be -3, 1. To this, we're going to add vector b, and its components are left 1 and down 2. So its components are -1, -2. And then we add the vectors by simply adding the components, just like we would as if we were just adding two matrices, giving us -4, -1. Now visually what's happening here, when you add vector b to vector a, you make a chain of vectors to figure out the resultant vector. So starting with vector a from tail to head, and then take vector b and position it so its tail is at the head of vector a, and it takes you to a new location. And the vector that is the sum will be the vector that connects the tail of A to the head of where B now is. So this green vector has components, start at its tail, go left 4, and then down 1. So -4, -1 would be the components of this green vector. Subtracting vectors, you simply subtract components. This would give us -3 minus -1, -3 plus 1, which is -2, and then 1 minus -2, which is 1 plus 2, or 3. Subtraction of vectors can be thought of as addition with an opposite. So you can think of a minus b as being vector a plus the opposite of vector b. So I'll make vector -b, and then originate this vector at the head of vector a. Connect the tail of vector a to the head of where the negative of vector b currently is, and we have the vector a minus b. Notice the components of the green vector would be left 2, followed by going up 3. So -2, 3, which is exactly what we got when we subtracted the components. A plus 2b is found by doing vector a and adding to it the double of vector b. So double the coordinates of vector b, so its coordinates would be -2, -4, and now add components. So we get -5, -3. Visually, we would take vector b and double its length while preserving its direction, giving me the vector 2b, and then add this, originate it at the head of vector a, giving me the green vector a plus 2b, whose components would be left 5, down 3. And then finally, a third of a minus a half of b. Multiply the components of a by a third, so we get -1 and a third. Subtract from this, multiply the components of b by a half. That would give me -1/2 and -1. And then subtract component-wise, and we get -1 minus -1/2. That's -1 plus a half will be -1/2. And 1/3 minus -1, that's 1/3 plus 1, will be 4/3. Visually, we take a third of a half of b, change the direction of 1/2 b, and then put this vector, originate this vector at the head of 1/3 a, giving this green resultant vector whose components are left 1/2, up 4/3. Okay, let's go to the next page. A unit vector is a vector with a magnitude of 1. Any vector v can be scaled to become a unit vector, u, with the same direction as v as follows. Take the vector v and scale it by 1 over its magnitude, and this will produce a vector whose length is 1. So in these cases, we first must find the magnitude of the vector, which will be the square root of the sum of the squares of the components, so 1 squared plus 3 squared, and we get radical 10. And then we take the vector a and basically divide every entry by its magnitude. So we get 1 over radical 10 and 3 over radical 10. This vector has the exact same direction as the vector a, but its magnitude is 1. So here's a unit vector that points in the same direction as a. If you wanted to do a unit vector that points in the opposite direction, then you simply have to do the opposite of this. And here's a unit vector, a vector whose length is 1, but it points in the opposite direction as vector a. Now let's look at vector b. This vector points left 2. So we can easily deduce that its unit vector, pointing in the same direction, should only point left 1 unit, and the opposite direction should point right 1 unit. Well, let's confirm. The magnitude of vector b, it's the square root. Square the negative 2, we get 4. Square the 0, 0. Takes us back down to 2 as a magnitude, which is not surprising for a vector that only points 2 units to the left. And then calculate b, the vector b divided by its magnitude. So divide all components by 2, we get negative 1, 0. So here's a vector that points in the same direction as b, but its length is only 1. And then the opposite of this will be a vector whose magnitude is also 1, but points in the opposite direction as b. For a three-dimensional case, we do the same thing. The magnitude of the vector c is found by doing the square root of the sum of the squares of the components. So 5 squared is 25, plus negative 1 squared is 1, plus 3 squared is 9. So this gives us radical 35. Divide every entry by radical 35, and we get a unit vector that points in the same direction as c. So 5 over radical 35, negative 1 over radical 35, and 3 over radical 35. And then, of course, the unit vector pointing in the opposite direction as c is the opposite of this vector. In this 3D case, I encourage you to plot the original vector as well as both of these unit vectors to make sense of what you are seeing. Now, the standard basis vectors are unit vectors that point in the direction of increase for each component. Identify these vectors for both 2D and 3D spaces. So vector I, is a 2D vector that points 1 unit in the x direction. So its components would be 1, 0. The j vector is a unit vector, so length 1 unit, but pointing in the y direction. So 0, 1. In 3D, the I vector will be the vector of length 1 pointing in the direction of x, so 1, 0, 0. The j vector will be 0, 1, 0, and the k vector will be 0, 0, 1. These standard basis vectors give me an alternate way to write a vector. For example, express the 3D vector below in terms of standard basis vectors. So first of all, we can pull this vector apart by components. We begin by decomposing the vector into its components in the following way: 5, 0, 0 plus 0, negative 1, 0 plus 0, 0, 3. And you can clearly see that when adding these vectors together, you will get 5, negative 1, 3. And then you factor out the constants, giving 5 times the vector 1, 0, 0, minus 1 times the vector 0, 1, 0, plus 3 times the vector 0, 0, 1, which you can write in terms of I, j, and k as 5 vector I minus vector j plus 3 vector k. So when a vector is written as a sum of standard basis vectors, the coefficients of I, j, and k are simply the components of the vector. Okay, let's go to the next page. The dot product of two 2D or two 3D vectors is a scalar resulting from matrix-matrix multiplication as shown below. So when you see a dot between two vectors, such as this, then we are doing what's called the dot product. One way to think of the dot product is is to do the transpose of vector u and then multiply that by vector v. So when we think of this as matrix-matrix multiplication, this is a 1 by 2 matrix multiplying by a 2 by 1 matrix. So this matrix-matrix multiplication is defined, and we should get a 1 by 1 back, which is a scalar. This matrix-matrix multiplication yields the product of the first components plus the product of the second components. And the 3 by 3 case is similar. We have a 1 by 3 multiplying it by a 3 by 1. This should give us a 1 by 1, and it will be the sum of the products of the corresponding components. Find the dot products below. So I presented the dot products in a variety of ways. If you like, you can rewrite these in different notations. So negative 2i plus 2j is the vector negative 2, 2. We're going to dot product that with the vector I plus 3j. I plus 3j has components 1 and 3. And then to find the dot product, we multiply the first components and get negative 2, and add to that the product of the second components. 2 times 3 is 6. And we get 4. Okay, the second example is just a disguised dot product. It's the product of the transpose of that vector 2, negative 3, which would look like a row vector of 2, negative 3, multiplied by a column vector of negative 2, 0. This will give us a 1 by 1 result. Negative 2 times 2 is negative 4, and then negative 3 times 0 is 0, so we get negative 4. The third case is already presented, so that matrix-matrix multiplication can be done right away. We get 2 times 3 is 6, and then plus 2 times negative 3 plus negative 6, and we get a dot product of 0. In the third case, we have a dot product of two three-dimensional vectors. 5 times negative 1 is negative 5. 2 times negative 1 is negative 2. And 4 times 3 is 12. So we get 12 minus 7, and we get 5. Find the dot product of a 2D or 3D vector with itself. Describe your findings. Let's explore a dot product of a 2D vector with itself. So we would multiply the a and get a squared, and to that add the b and get b squared. In a three-dimensional case, the dot product of a vector with itself, we multiply the a and get a squared, the b and get b squared, and the c and get c squared. This establishes a connection between magnitude of a vector and the dot product of that vector with itself. In the following way, I could square root both sides. So the square root of a vector dot product with itself is equal to the square root of the sum of the squares of its components. Well, that is simply its magnitude. So I could then square both sides and say the following statement. A dot product of a vector with itself will always equal the square of its magnitude. Same thing is true in this three-dimensional case. The dot product of a vector with itself will be equal to the square of its magnitude. Okay, let's go to the last page. Suppose theta between 0 and pi radians, or 0 and 180 degrees, is the angle between two 2D or two 3D vectors when their tails are in the same position. The following equation relates this angle to the dot product. We won't prove this, but the dot product can be shown to be equal to the magnitude of the two vectors involved times the cosine of the angle between them. Now mind you, when you have two vectors of the same, with the tail in the same position, this forms an angle which technically has two measurements. There's the shorter angle measurement, and then there's the outer or larger angle measurement. The angle in question here in this formula is the green angle. It's an angle that will vary between 0 and 180 degrees. Find the angle in degrees or radians between each pair of vectors. Then plot the pairs of 2D vectors. In this first case, let's find the dot product of the two vectors. Multiply corresponding entries. We get negative 2 plus 6, and we get 4. Now we've got to find the magnitude of each vector. The magnitude of vector u is equal to the square root of square the two components, so that gives us 4 and 4, and add together, and we get square root of 8. The magnitude of vector v, square root of square the 1, square the 3, add together and take the square root, we get radical 10. So according to our formula, the dot product will be equal to the product of the magnitudes times the cosine of theta. We can solve this for theta by dividing by the two radicals and using an arc cosine. So theta is equal to the arc cosine of 4 over rad 8 rad 10. I'm using the Desmos calculator to calculate this. So type in arc cosine of 4 over square root, and we can multiply rad 8 and rad 10 and get rad 80. And it gives me an answer. Now this answer is in radians. In Desmos, to change this to a degree answer, click over here in the right on graph settings and switch this to degrees. I'll give my answer in degrees. So approximately 63.4 degrees. Let's go ahead and graph both of these. I'll put the origin right there. So vector u is left 2 up 2, and vector v is right 1 up 3. And I'm positioning them so that their tails are in the same location. The angle that we found was this acute angle right here, and it is about 63.4 degrees. Okay, the second pairing, I'm using bold letters to stand for vectors now. But when I write by hand, I'll switch to the arrow notation because writing bold letters by hand can be tedious. So begin by finding the dot product of a and b. We multiply the first components, which are the coefficients of the I vector. So 2 and negative 2 multiply to negative 4. And to that we add the product of the j coefficients, so negative 3 and 0. And we get negative 4. Now the magnitude of a is the square root of square the 2, square the negative 3, add together radical 13. And the magnitude of vector b is going to be 2, because b is just 2 units to the left. Therefore, in this case, theta will wind up being the arc cosine of negative 4 over 2 rad 13, which is about 123.7 degrees. Graphing both of these vectors, vector A is right 2 down 3, vector B is left 2, and when they originate from the same point, the angle we just found is this angle right here, and is about 123 degrees. We call this an obtuse angle because it is more than 90 degrees. And in the first case, we call that an acute angle because it's less than 90 degrees. Third case, the dot product of w and z, multiply the first components, get 6, multiply the second components, we get negative 6, combine those, and we get a 0 dot product. Therefore, in this case, theta will wind up being the arc cosine of the dot product divided by their magnitudes. And it doesn't really matter what their magnitudes are, because 0 divided by them will still be 0. And the arc cosine of 0, so we're trying to think of the angle between 0 and 180 degrees at which the cosine is 0, and that's at angle 90 degrees. Plotting these two vectors, vector w is 3 to the right, 2 down. Vector z is 2 to the right and 3 up. And theta is a right angle in this case. Now, if you recall from trigonometry, the inverse cosine is a function that has a limited range. It will only output angles between 0 and 180 degrees, which is exactly the range that we want for theta in the first place. Thus, we will never need to adjust our calculation of arc cosine in order to get a correct angle given the context. Furthermore, the arc cosine of a positive number will wind up giving an angle in the first quadrant, hence an acute angle. The arc cosine of a negative number will give an angle in the second quadrant, which is where cosine is negative. So we'll give an obtuse angle. And the arc cosine of 0 will give 90 degrees, suggesting that the two vectors are in fact perpendicular. Thus, we can generalize if the dot product is positive, the angle between the two vectors should be acute. If it's 0, it should be 90 degrees. And if it's negative, the angle between them should be obtuse. This formula also works for three-dimensional vectors. First, we'll find the dot product of x and y. Multiplying the first components, we get negative 5. Multiplying the second components, we get negative 2. Multiplying the third components, we get positive 12, giving us a dot product of 5. Now, the magnitude of vector x is the square root of, and then square each component, add together. So negative 1 squared is 1, 2 squared is 4, and 4 squared is 16. So we get radical 21. The magnitude of vector y is equal to the square root of 5 squared is 25, negative 1 squared is 1, and 3 squared is 9. So we get radical 35. And we wind up getting that theta is equal to the arc cosine of the dot product, which was 5, divided by each of these magnitudes, rad 21, rad 35. And technology gives us an answer that is about 79.4 degrees. I will use the 3D plotting software to plot both these vectors. I added to graph two different vectors, entered the coordinates and changed their colors and made sure that they were visible by checking these boxes, and we can see the two vectors present here. Rotating this gives us different angles to look at the two vectors, but the angle between them, the angle from red across the same plane that both vectors are in to blue, and the shorter angle right here, is the 79.4 degrees that we calculated using our formula. Okay, and this concludes our lecture on vectors.